Welcome, my friends. In this video, I will be discussing sections 6.3 and 6.4, linear regression and the coefficient of determination. Our goal is to draw the line that fits the dots the best on the scatter plot. But what do we mean by best? Maybe I might draw line number 1 through the scatter plot, and maybe someone else would draw line 2. So how do we know whether or not my line is the best, or your line is the best, or maybe some other line is the best, right? So my point here is that anyone can just draw what they think is the best line through a scatterplot, and we would like to have a more objective way to define what is meant by the best line. So maybe you can pause the video for a minute here and think about how could we determine whether one line is better than the other, and how could we actually construct the best line. So that's what we're going to talk about here on the next slide here. So here is another scatterplot, and in this scatterplot I have drawn the best line, what we would actually call the best line. And I've also kind of represented the distance between each dot to the line with each of these lines here. And I have a couple of things that I need to kind of define here before we get to the criteria we're using in order to determine which line is the best. And first of all, we're going to use y to represent each y coordinate of each of these points. So for example, the very first y coordinate, or the first y value, is looking like it's at about 28. That's this one right here. Or the next one is looking like it's about 15, etc., right? So whenever we talk about y, we're just talking about the y coordinate of each of these different dots. And we differentiate that between what we call y hat, y with a little kind of caret on the top, and that represents the y coordinate corresponding to the line related to each y point. So each y also has a corresponding y hat value, which is also going to be representing a predicted value. So the line is oftentimes used, as we'll see later, to make predictions. And in this case, the first y hat value is at about 21. So the first y is at 28, but the corresponding point on the line would be 21. The residual is the difference between those two numbers. So if we take the actual y value, or the y point, and subtract the value on the line, y hat, or the predicted value, then we will get the residual. And the residual is represented by this vertical distance here, this line from the dot down to the line. And the first residual is 28, the y value, minus the value on the line, which is 21, and we get about 7 for our first residual, which really just tells us that if we were to make a prediction for this value here based on the line, the prediction would actually be 7 off, or it would actually be below the actual value by 7. Now, we also have to sometimes square these residuals. This is going to become, you'll see why this is important in a second. So if we were to square the first residual, that would look like this. So we would take the y value, we would subtract y hat, that's the residual, and then we would square it. And so in this case, we would get 49 for the first squared residual. The first residual was 7, and if we were to square it, we would get 49. 7 squared is 49. Okay, so that brings us to the idea of the criterion that we're going to use for the best line. So what makes this the best line? And you might have thought it's just the line that is minimizing the distance from each dot to the line, like the vertical distance here, but it's a little bit more complicated than that. Is actually minimizing the squared distance, or the squared residuals. So here's the definition that I'm giving. Linear regression is the process of finding the best line, which is what we call the least squares line, which has the smallest sum of the squared residuals. In other words, if I had this line and I calculated every single residual, I squared each one, and I added them all together, if this is the best line, then there's no other line that I could use that would have a smaller sum of all those squared residuals. So I know it's a little bit technical there, but that is the criteria that we use in order to draw the best line through the scatterplot. And we call this linear regression, or the line itself is called the least squares line. Now, I should also just mention that the sum of the squares residuals actually has a name. We call that the sum of squares error, sometimes abbreviated as SSE. And the formula for that would be the sum of each y values. We say y sub I minus y hat squared. Basically, find each residual, square them, and then add them all together. Okay, so the equation of the line that we're going to use in this class is going to be y hat is equal to a plus bx. So y hat, like we said on this slide, that's going to be the line, right? Y hat is representing the line. And we're going to call that a plus bx, which is very similar to y equals mx plus b that you may have seen like in an algebra class. So y hat is the line itself, and that's going to be representing the predicted value for y. Eventually, we're going to use this equation to predict a value for y based on x. So some people ask, why don't we just use y? Why isn't it just y equals a plus bx? Well, because y, we already said, is each of the points, right? And this line is not actually going to find us each of the points. It's really just going to give us a predicted value for each of the points. The a value is what we call the y-intercept. That's where the line is going to intersect the y-axis. B is what we call the slope. It kind of indicates how steep the line is going to be and whether or not it's going to be upward sloping or downward sloping. And then x is going to be the value of the explanatory variable that is used to predict y. Now, when we eventually create the equation, we'll have a value for a and a value for b, but x will stay as a variable in the equation. So it'll be something like y hat equals 30 plus 7x or something like that. And then you can plug in a different value for x. Now, if you want to do this by hand, it's quite involved. So instead of using the by hand formulas or showing you the by hand formulas, we're going to be using the TI-84 calculator instead. Note that if you're following along with the Grand Valley textbook, you'll see they use a slightly different form of this equation. Instead of a plus bx, they use b sub 0 plus b sub 1x. But I'm going to be using this notation here because it matches the TI-84 calculator output. All right, so here's an example of a data set. We have the hours studied as our x variable and the exam grade, which is our y variable. And it's very important that for this type of data that each variable is calculated from the same person, right? So person number 1 studied 0 hours, and person number 1 also, that same person, got a 57 on their exam. Or this third to last person studied 8 hours and scored a 79. And all those values have been put on this scatter plot. So our goal here is going to be to find the equation of the line that fits the dots the best. So how do we do that? Well, we can go ahead and grab our calculator. And the very first thing you're going to want to do here is you're going to actually want to run a setting so that we get all the output that we need. Because if we don't run this setting first, we're not going to get the correlation coefficient that we talked about in a previous video. And we want to have that as well. So to run the setting, we can press the second key. And then 0 will get us to the catalog of basically all the different functions and options in the entire calculator. And then we can go to the D's by doing this x -1 key. And that'll get us to the D's. And then if you scroll down, you will eventually see an option that says diagnostic on. So press enter over that one and press enter one more time. The calculator will just say done. And that way you know you've ran the setting, and whenever you run regression, you're going to get all the output that you need. You should only ever have to do that once per calculator. So as long as you use this calculator in the future, you should always never have to do this again. Okay, now we can go into our stat list, and we can go into edit, and we can go ahead and enter in these numbers, which I'm going to do right now. All right, I got my numbers in here, and I strongly encourage that you follow along. So I would pause the video and type those numbers in yourself if you haven't done so already. But now we can go to the stat menu again, and we're going to want to arrow once to the right so that we're on the calculate menu. And then we're going to want to go down to option 8. You'll notice option 4 is also linear regression, but we want to use the 8th option here. And this is going to give it the same way that I've represented in the slides. Otherwise, the A's and the B's are mixed around. So I'm going to use option 8. Make sure it says list 1 and list 2 if you're prompted with this. Some of you might not even be prompted with this. You can just press enter. But make sure it says list 1 and list 2. If not, you can change the list by pressing second and the number of the list that you want. Go down to calculate, and then we will have the output that we need. Now, note that the calculator does list it as y rather than y hat, but it really should be y hat. So it should be y hat equals a plus bx. And they give us a whole bunch of information here, which we're going to kind of dive into in the next few slides. So here are the instructions kind of written out that we just did. And here is that same exact output. Let me check to make sure it's the same. 61.73, yes, 3.05. Yeah, it looks like we do have the same numbers. Okay, so the regression equation is y hat equals a. A is this number, 61.73, plus bx. B is 3.0527 times x. And I typically take the b value to 4 decimals and the a value to 2 decimals. You can take more if you want to, but this is just usually what I do. Now from here, we want to be able to interpret or understand all of the information that is coming here. So first of all, this is the equation of the line. If you were to graph this line, it would be the line on the scatter plot that would fit the dots the best. And they also give us the correlation coefficient here, which is r. So I'm going to give you a template statement that you should use to explain or describe the correlation. And this is what we're going to use. We're going to say there is either a weak, moderate, or strong positive or negative relationship or correlation between our x and our y variables, where anything in brackets is where you're going to have to kind of customize that to your specific problem. And if you remember anything about the correlation coefficient, you know that the closer it is to 1 or -1 is going to be indicating the stronger relationships, and the closer to 0 is going to be like a weaker relationship. Positive or negative is determined by the sign, positive or negative here, and then we would describe our two variables. So in this case, the 0.7749 value that we have would say that there is a moderate, since we're kind of we're maybe moderate to strong. We're not quite in the strong range, like 0.77. It's kind of like moderate to strong. We're in the moderate range. We say there's a moderate positive, because the number is positive, correlation between our two variables, which are hours studied and the exam score. And we also have one other value here, which is r squared. So this is what we call the coefficient of determination, which literally is r squared. So if you took this r value and you multiplied it by itself, or squared it, you would get this r squared value. And this r squared value can be interpreted in this way. So first of all, we're going to represent it as a percentage. So r squared percent of the variation in your y variable can be explained by your x variable. So what I mean by variation is kind of like how much those values vary. So here's our y variable, and there's a lot of variation in those numbers. They're not all the same. There's variation in these numbers. So what explains that variation? Well, one thing that helps explain that variation is our x variable, but it doesn't explain necessarily all of that variation. There could be other variables that could explain more of the variation. But hours studied alone does explain, or get you part of the way to explaining why the exam grades are varying. So in our example, we would say that 60.05%, that's the percentage form of r squared here, of the variation in our y variable, which is the exam scores, can be explained by the x variable, which is the hours studied. Okay, one other thing that we can interpret is the slope, which is the value of b. And here is the interpretation that we will use for the slope. It says that for a 1 unit increase in our x variable, the y variable is predicted to either increase or decrease by the positive version of the slope. This is the absolute value of the slope, right? And so in our example, we would say for 1 additional hour of studying, that's a 1 unit increase in x. X is the number of hours studied. So a 1 unit increase in x would be 1 additional hour of studying, right? The y variable, which is the exam score of a student, is predicted to increase, since we had a positive slope, by 3.0527 points. Now, if you had a decrease, then you would still use the positive version of the slope. So let me show you an example of this. So let's say this was an equation, and this has a negative slope, right? So then you'd say, if this was the case, for 1 additional hour of studying, the exam score of a student is predicted to now decrease by 3.0527 points. Make sure you don't use the negative sign if you have a negative slope, because kind of the word decrease is already doing the work of the negative. Now, this interpretation probably wouldn't make a lot of sense. This probably wouldn't be our equation, because it doesn't make sense for more studying to lead to a lower score. But theoretically, in many cases, you could have that negative correlation. Okay. So please resort to these interpretations for the slope and for the correlation coefficient and the coefficient of determination. And please study these and understand how to use these, because this will be one of the major things that I ask you with relation to regression, is not just get the output, but making sure you can write a sentence explaining what some of those numbers mean. So please come back and use these templates when you're doing that. Okay, there's a couple other things that we can do. So we said that the equation is used to make predictions. So basically, now that we have this equation, we can plug in any value of x that we want to, and that will give us a prediction for y. So x, remember, is the number of hours studied. So let's say we want to predict the score of a student who studied for 10 hours. Well, to do that, we can just plug in 10 for our x variable. So we would have 61.73 plus 3.0527 multiplied by 10. And if you plug that into your calculator, you'll see that you get about 92.257. So that says if a student was to study for 10 hours, then we would predict their exam grade to be about a 92. What about a student who studies for 40 hours? So maybe you're the overachiever and you just go out there and just study all night. Have you ever studied 40 hours for an exam? Man, I have. I've had some really big exams that I had to take in grad school, etc., that were very, very long, and I studied for weeks for some of these things. And so what would our exam grade be, or our predicted exam grade be for 40 hours of studying? Well, we can go ahead and plug 40 in. We get 61.73 plus 3.0527 times 40, and we get 183.838. So we would predict the exam score for a student who studied for 40 hours to be 183.838. And you would stop and say, well, wait just a minute. Wasn't the exam out of 100 points? And you would be correct. Yes, the exam is actually only out of 100 points, so this doesn't really make a lot of sense. So what went wrong? So maybe just think about that. Why did this not work? I mean, we had a pretty strong correlation here, a moderate to strong correlation, so we would think that we'd be getting pretty decent predictions. Well, that brings us to the distinction between interpolation and extrapolation. So interpolation is when you're making a prediction for your y variable using a value of x that is within the range of your initial data set. So in other words, if you plug in a value of x that's anywhere from 0 to 12, then that would be considered interpolation. You're plugging in a value of x that's within the initial range of your data set. And if you make a prediction using interpolation, then that's likely going to be an accurate prediction as long as you have a relatively strong correlation, right? So the stronger the correlation, the better. But as long as you have maybe a moderate to strong correlation, then you can expect that if you're interpolating, you're going to have a relatively good prediction. On the other hand, if you are extrapolating, that means that you are making predictions for y with values of x that are not within the range of the initial data set. Note this all depends on x, so what value that you're plugging in for x. So now if I'm plugging in a value of x that's not between 0 and 12, maybe bigger than 12, like 40, like we had a second ago, right? Or even just like 15 or 20, right? Then you can expect that those predictions are not going to be quite as accurate, even if you have a strong correlation. Now, of course, some people would ask, what if I plug in 13? I have 0 through 12. What if I plug in 13? Well, you're still technically extrapolating, but at that point, you're so close to the range of the data set that you might still expect that prediction to be relatively accurate. But as soon as you start going a little bit farther, 15, 20, 25, you can expect that your model may break down. Really, the model was only built for hours of studying of 0 to 12. So if you start feeding it things that are outside of that range, you can't really expect to get a good prediction. Okay, so here is what the line would look like on the scatter plot. So we have our y-intercept, which was 61.73, you might remember, which is kind of where we intersect the y-axis, and then the slope is 3.0527. Now you can create this on your calculator. So if you go back in here, and you go back to stat, arrow to the right, and you do the option 8 for linear regression, and you go in here to the store reg EQ. And then let me make sure I can get this right here. I think it is under vars. Yes, vars, and then yvars. And then the option for function. And then it'll give you the option for y1. And then when you go ahead and calculate, it will put that into your y1, the equation. So now I can see the equation is in there. And then you're going to want to go to second and y equals. Enter. And make sure you have plot 1 on. And then you can change this to the scatter plot if it's not already selected. L1 and L2, and then you can press second and L2 if it wasn't saying the correct one, or second or an L1. And then when you do zoom and 9 to do the zoom stat, it's going to give you the picture of the scatter plot. So we can kind of get the same picture there if you'd like to on your calculator. Okay, we've already talked about this to some extent, but the residual is the difference between the actual y value and the predicted y value. So here's what all the residuals look like in a table based on our data set. So we have the hours studied. The first two columns are really just the data set that we had, the hours studied and the exam grade. And then I've done the prediction for every single one of those. So in other words, I plugged in x into the equation, and I got each of these different numbers out. So when I plugged 0 in, I got this. When I plugged in 2, I got this, etc., all the way down. The residual, as we talked about before, is y minus y hat, or the actual value, this column, minus the predicted value, which is this column. So now I have the residuals for every single one of these. And any of the negative values are going to actually represent over predictions, and any of the positive values are actually under predictions. So for example here, the prediction was 61.73, which is higher than 57. So this is an over prediction by 4.73. Or let's look at a positive one. So this one, the actual value was 76.99. The actual value is 82, but the predicted value is 76.99, so we actually underpredicted. We predicted lower than 82 by 5.01. So any of the positive residuals are going to represent underpredictions, and negative are going to be overpredictions, which might be a little bit backwards of what you would expect in your head. Graphically, here's what the residual kind of looks like here. We've already kind of explained this. It's really just the distance between the dot and the line, right? So in this case, if the predicted value was 70.2, y hat is that would be on the line. The distance from there to the point of 59 is 11.2. And based on the direction that we're subtracting these, we take the actual value and subtract the predicted. We get negative 11.2. Which represents an over prediction in this case, right? We predicted 70.2 for looks like a final exam, but the actual score was 59. So remember, the residual is just the distance from the point to the line, or y minus y hat. Okay, so here's a problem for you to try. So let x represent the high temperature in degrees Fahrenheit, and y represent the number of coffees sold at a cafe in a day. And let's say I just give you the equation here. The equation is 45.313 minus 0.569 times x, right? So go ahead and see if you can do these three things here. So see if you can interpret the slope, use that template statement from earlier, predicted number of coffees sold for a day when the high temperature is 37 degrees Fahrenheit, and then if the actual number of coffees sold on that date is 27, find and interpret the residual. So go ahead and pause the video and give those three a shot. Now I'm going to go ahead and go through the first two. So hopefully you've given these a shot here, but I will give you the answers to the first two, but not to the third one, because that is going to be the one on the video quiz. So interpret the slope. So we're going to use that same template as before, which said for a 1 unit increase in x. That's the first thing here, right? And x in this case is the high temperature in degrees Fahrenheit. So in a 1 degree increase in it should say maybe high temperature, in the temperature or high temperature in degrees Fahrenheit, the x variable, which is number of coffees sold in a day, is predicted to decrease by the positive version of the slope, which is 0.569. Don't say decrease by negative 0.569, then you have a double negative. It's just going to be decreased by 0.569. Number 2 asks us to make the prediction. So if we want to predict when the degrees are 37, we can just plug in 37 to the equation. We should get 24.26. And then to find the residual, we would just take the actual y value, which they're telling us is 27, and subtract the predicted value. And then interpreting that would be, it's either going to be an over or under prediction. I'll let you determine that for yourself. All right, we're basically done here. I just have one more problem here for you to try, and this is relating to a number of different countries, their GDP per capita in thousands of dollars, as well as the infant mortality per 1,000 live births. So keep in mind here that these are in thousands, so this is not actually 1.2, this is 1,200. This is not 4.2, this is 4,200. You can still type it in your calculator with the decimals here. Just know that anytime you're thinking about x, they're going to be in thousands, right? And these are numbers out of 1,000, right? 65.2 out of 1,000 deaths per live birth in Guinea, or etc. for all the other ones, right? So go ahead and type those numbers into your calculator, run the regression, get all of this different information, and then finally you'll have to make a prediction here. When it asks if you should rely on the prediction, you should be considering two things. One, are you interpolating or extrapolating? And secondly, how strong is the correlation, right? So those two things should go into determining whether or not you should rely on the prediction. You can also sometimes consider how reasonable does the number seem. So if you get a number that seems to be unreasonable or maybe not even possible, that would also lend weight to maybe it's not a great prediction. But that's all I had to talk about in this video, so I will see you in the next one.